Controlling a brushless motor's ESC with a PWM signal, today on Mikey's Lab. Alright, so today we're looking at controlling a brushless motor through an ESC using PWM from an Arduino. Okay, we've started capitalizing, give ourselves a little bit of a head start by reusing some of the code from consuming an iBus signal so that we have the ability to give a signal to the motor. So what we have in our setup here, we have the Arduino here, which has our software that we'll take a look at in a minute loaded onto it. We have an A8S receiver. We have a voltage regulator that takes the 9 volts that I'm feeding from my bench power supply up to 15 amps to mimic a LiPo battery pack. It just makes it a little safer for us to work with because we have the short circuit protection over current protection that comes with my benchtop power supply. And turns that into 5 volts for the Arduino and for the receiver. And we have an Emax RS2205 2300 kV motor. Now this came from one of my drones. Back in the day, these motors were all the rage for drone racers. So this is probably the best motor that we can use to for our combat robot. So what I'm going to do is, the very first thing is I'm just going to power this up, and we're going to show that it does work the way that I think it works and that it auto reverses. And then we're going to go take a look at the settings that I set on this ESC, and we're going to take a look at the source code that we're using to control it. So lab code up. We're going to learn something today. So let's go ahead and turn the lab power supply on. And you immediately hear the ESC initialize. And we'll turn on the controller, and you hear the other initialization beeps. What's going on at that moment will become much clearer when we look at the source code, but there is a PWM pattern that you have to use in order to initialize the ESC. But if I go forward, you see that the motor does start to spin in one direction. It's hard to make this go slow enough that you can actually see which direction it's spinning in. Alright, and if we go backward, it goes in the other direction. Now for those of you that are hearing the noise of the motor and saying that sounds crunchy, this is an old motor. This one has been through several crashes on Scout. It was the first one that I grabbed off the shelf. The other ones are in better condition. We're obviously going to use the better condition ones for the actual project that we're working on. Now that we see that we can control both speed and direction of the motor, let's take a look at how we did this. So we're going to drop to the computer. Alright, so here we are in Visual Studio. For those of you that don't remember, I have a plugin for Visual Studio. I do all my Arduino programming inside of Visual Studio called Visual Micro. All of this code can be copied and pasted into the Arduino interface, Arduino programmer, and it will work just fine. The only reason that I use the Visual Studio plugin is I love the syntax highlighting, I love the autocomplete, everything that was missing from the Arduino IDE. It is very, very possible that the best programming IDE in the world is Visual Studio, and I am not a Microsoft fanboy. They just did a wonderful job. Okay, so in our last video, we took a look at installing BlHeli and upgrading and changing the settings of these little B ESCs, right, using an Arduino. It's very important that we understand the settings that are on these, so let's go take a look. I did take a screen capture of the settings that I used, so we're going to go ahead and take a look at that right now. Alright, so these are the settings that I have in here. You can obviously see that they're bi-directional. I do have a closed loop mode enabled. It's kind of a light one. That brings a PID loop into the controller itself. I don't know if it's really necessary for this application, but it's what we have. The things that matter the most is the PPM min throttle, the PPM max throttle, and the PPM center throttle. Now, when they say PPM, we can just translate that to PWM at this point. And these are the values that go, the ESC is expecting in order to have a set amount of power going to the motor. So min throttle is obviously anything below 1080 and it's just not going to spin. Center throttle is important with the bidirectional mode because it tells the ESC when to switch directions, which at this one is 1488. You'll see how we address that in the code in a minute. And PWM max throttle 1852 basically is throwing the max voltage at the motor at 1852, and anything higher really doesn't have an effect. Now that we've taken a look at the settings that are on this ESC, again being BlHeli, right, version 14.9, which is the highest that this ESC can handle, but how we are talking to the ESCs via PWM will work with any version of BlHeli. Alright, so now we're going to take a look at the software for this project. There's pieces in here that are for consuming the iBus signals, so we are going to go ahead and just ignore those for now and deal only with the side of controlling the ESC. So the first thing we start off with is, in most of my projects, is a series of defines. So we have ESC min throttle, which is 1070, we have ESC max throttle, which is 1852, and we have ESC reverse throttle, which is 1488. Now, first thing you're going to notice, this is slightly different than the version or the values that were in the BlHeli configurator. This is intentional. I want to send signals that are outside of the range so that we have a buffer at the minimum and at the maximum. So 1070 is where we're going to start the minimum throttle, which will obviously not have the ESC spinning at all. The next define is the Esc Arm Signal, which is 1000. For those of you who are not familiar with the way these ESCs work, since they're designed to go onto aircraft, you don't want them to power up unless you specifically are telling them to power up. So they have an arm signal. This is definitely one of the things that differs between controlling, let's say, a DC motor through a motor controller and or a standard brushed DC motor through a motor controller and a brushless motor through an ESC. So the arm signal we have to send is 1000, which, if you understand how PWM works, is the lowest signal possible. And we have an arm time of 2000 microseconds. So we have to hold that 1000 signal for 2 seconds in order to arm the ESC. Prior to that, it will not respond to signals that are given to it. This is a safety feature designed for aircraft. The next thing we do is we define ESC pin 1, which is our ESC 1 pin, which is 8. This is the pin that is attached to. It's very important when you choose the pins that you're going to control an ESC with that you think about the PWM capabilities of the pins you're using. Hardware PWM is much better than software PWM, so the Arduino does have several pins that are capable of it, so let's use those. The next define that we have is Esc Deadzone Range. What this is the ESC will stop spinning at 1488 signal. Now, we don't tend to stay around the 1488 signal. We flutter a lot. So I wanted a dead zone in the middle to make sure that when I let go of the stick, the motor just stops. This is very similar to what the flutter range is. The dead zone is fixed in the center, so it will be 1388 to 1588 with this setting. Flutter is not changing the value that we are sending the ESC unless we intend to change it by more than 10. So those two kind of act as a filter. The next couple of defines are for the iBus implementation, which we don't need to look at right now. There will be another video coming up on the newer version and the optimizations I've made to that. Next thing we do is we include a servo library. Now, everybody might be saying, well, why are we including servo? Well, a servo uses PWM, the 1000 microsecond to 2000 microsecond pulse, in order to set a position. An ESC uses the same pulse in order to set a speed. So we're just going to go ahead and take advantage of the existing library that's built into Arduino to deal with servos and reuse it to deal with the ESC. The next values are for consuming the iBus. Again, look for a future video on how I've changed what we do. RC scale value we'll talk about in a minute. And then we define an instance of servo and we call it ESC. That's just basically instantiating the library and allowing us to work with it. and we enter this setup function. Now, those of you who've worked with Arduino before know the setup function runs once at the boot up of the Arduino. So we start our serial connection. This identify is something that I've been doing more recently. If we go to definition, we just basically write out the firmware file that is burned to the ESC, the date and time that it was done. I have spent and lost hours troubleshooting a system where I thought a specific firmware was on the Arduino and it wasn't, and that brought no end of stress to my life. So we've added this so that on almost all of my Arduino projects, so the first thing the Arduino says over serial is what file name was burned and what date and time was it burned. So we go back, and then we just say initializing to whatever might be listening, and we call ESC attach. Now what this does is it attaches the PWM functionality and the Servo library to a specific pin with a minimum value and a maximum value. So in this case, it's going to be ESC pin 1, it's going to be 1070, and it's going to be 1852. And then we go into a function called Init Esc. Now, as I talked about before, the brushless motor ESCs are designed to be used in aircraft, and as such, they need to be armed. So we go through the ARM process in Init Esc, where we write the microseconds of the ARM signal, which in our case with the BlHeli is the 1000 microsecond signal, and we wait at least 2 seconds. Now, some people would be like, why are we not just using a delay here? Short answer, I hate delays. This allows us to do other stuff while we're waiting for this to go through. Right now, I don't have anything to do, but this is great for when you want something to wait at least an amount of time. So obviously, whatever you put in between these requires time to execute, right? But this will hold the ESC to the ARM signal for at least 2 seconds. It seems a lot more flexible to me. So we go back into the setup function. The next thing we have is RC scale value. Now this requires a bit of explanation. The values that we get from the FlySky controller or from any of the controllers that you could be using here, usually 1000 to 2000. Because it's a digital signal, that tends to be very exactly 1000 to 2000. If you look at our max throttle, which is 1852, and our min throttle, which is 1070, that is obviously not a 1000 range. So we want to take the signal that we're getting from the transmitter and we want to scale that to the throttle range that the ESC is willing to accept. So we take the max throttle, we minus the min throttle, and then we divide that by 1000, and then we divide that by 1000 and return that. And that gives us a scale factor in order to more precisely match the throttle value to the ESC speed value. And we go back into setup. We just tell whatever is listening that we're done. And like any other Arduino program, we immediately fall into the loop. Okay. We call readRx. Now this function we're not going to go into a whole lot of detail with because again it's the iBus implementation for reading iBus. All we're going to say about this is that once we have a complete packet, so we have all the information for every channel, we return true, right? And when we go back to loop, when we have that, we enter into this call here. Now I originally wrote it like this. This is probably a much cleaner way to write this code, but it is very hard to explain to somebody who is using this. So I broke it out into a couple more lines. So to get value raw, we just take in literally the raw value from the array of RC values. To get value speed, we then scale value raw by the value that we calculated in setup, and then we write the speed to the ESC. Now that is not as straightforward as someone might think. So if we go here, we have at this point created implemented our dead zone. So what we're looking for is, are we in the dead zone? So if we go to the definition of that, you can see that what we're looking for is the speed we're about to try to write to the Esc plus or minus the Esc Deadzone Range from reverse throttle. If it is, then we return true. If it's not, then we return false. But if we go back to the write value function, if it is true, we write the reverse throttle value to the Esc. The reason for this is the Esc is very picky about the stop point, and I wanted something a little wider for where the motor won't spin. So this gives us a 200 value range where the motor is not going to spin. Now, of course, I know you can do this in the transmitters. I prefer to do this wherever I have control. So if you build one into the transmitter that is less of a range than this one, then this one will win. If you build one into the transmitter that's higher than this one, then that one will win. Either way, we're going to ensure that we have that dead zone in the middle of the stick so that when you let go of the stick, the motor stops spinning. So the next thing that we do is we check the current speed that we are sending to the motor. Now this just works inside of the library itself and spits out a value from its memory. It's not capable of reading what the Esc currently believes it's at, but it can read what PWM value we are spinning out to the hardware PWM controller. And then if the speed is greater than or equal to speed minus flutter range or less than or equal to speed plus flutter range, we do nothing. So what this means is we also have a floating dead zone. What I found when I looked at the values coming in from the transmitter is that they tended just to wander. So if you have the transmitter at a dead value, so let's say you're using one of the knobs on your transmitter and you turn it to a value, theoretically you should be getting that same value over and over and over and over, but you don't. It changes slightly. And this was putting a little bit of twitching into the motor, and I didn't like that. So I implemented basically a flutter filter this way. So we are not going to change the speed of the motor unless we are changing it by at least 10. This is obviously set by the flutter range, so you can make it smaller or bigger. Now, if we passed all of that, we write the new value to the Esc, and we return to loop, and we start that whole process over. Now, I know there isn't a whole lot to this stuff here, but there is definitely some traps for new players. I figured I should show it off. This is going to be part of the combat robot, obviously, but yeah. So what we have here, we're looking at the actual effect of the code, and as you can see, pulse width modulation is not a misnomer. You can see that the pulse's width is literally being modulated to determine the value that's being sent as I change the value on the stick, and then the motor speed changes proportionally. Yes, I know my oscilloscope's not the greatest, and it's not a very stable signal. I don't know if the flutter is the signal from the Arduino itself, or if it's my oscilloscope interpreting it kind of weird. But sometimes whatever tool you can afford is the best you have. But as you can see, as the signal gets smaller below the stop zone, the motor goes in one direction. As it goes higher than the midpoint on the throttle, it goes in the other direction. So that again is how we control a brushless motor through an Esc with BlHeli programmed onto it using PWM. I am going to be doing some experiments using the oneshot protocol. These particular Escs do not support D-shot, but I may get a couple of new Escs so that I can do a video showing you how to control a brushless motor through an Esc using D-shot. Those videos are coming in the future. Of course, all of this is for the beetle weight combat robot that we're working on, so stay tuned for more videos from that. Thank you for joining me in the lab today. I hope you learned something, and we will speak again soon.